Recording in progress.
All right, so I'd like to continue with our lecture. Are there any questions regarding the separation of the partition function, which we discussed last? So just as a reminder, here's again our table of contents so far. We went through the introduction. We introduced the partition function using Boltzmann's simple arguments. We then considered a whole bunch of state functions, lastly, the entropy. And we are now in the fourth chapter where we are discussing the various degrees of freedoms, in particular with respect to energetically different modes, and how they contribute to the partition function. Now, what we have done here at the end of the lecture on Tuesday was to separate out the partition function based on the argument that we have different energy scales that can add up to the total energy, right? So there's an additivity assumption behind this separation of the partition function. In other words, if these different energy modes can be partitioned into individual terms, separate terms, your partition function can be understood as the product of partition functions where each partition function refers to only one mode. Now, with these nodes here, we demonstrated this. It's simply factoring, making use of the fact that my exponential function of a sum is the same as a product of two exponential functions, and then factoring out the corresponding terms. Now, we've shown this for two energy modes here, alpha and omega. Now, by induction, you can simply assume that the omega mode can be separated once more into two more modes, and then you can repeat the exercise. And like this, you will see that actually your total partition function can be written then as a product over all your modes, your energy modes alpha, of partition functions that are separate for each mode. Again, this only holds to the degree that to which your energy, your total energy, is simply a sum over energies coming from each of these energetic modes. Are there any questions regarding that? So this step is known as the separation of the partition function, and we can immediately exemplify this for what's known as the diatomic harmonically vibrating rigid rotor. So this is a well-established system, right? A little bit like the particle in the box, or the harmonic oscillator, or your hydrogen atom. In physical chemistry, these couple of words refer to a well-defined situation. In particular, you have a diatomic atom, and I can see the joy in your eyes as we are moving away from the ideal gas with just a single atom. Now we have two per molecule. Isn't this amazing? And you can have obviously two different elements here, right? And now we have an internal degree of freedom, the distance r between these two elements. And we also have some mass 1 and some mass 2. Okay, so the mass is basically your isotope of choice of the element corresponding to atom 1 and 2. Now, it's a bit weird. We are saying it's vibrating and it is rigid. What this basically means is that there's no rho vibrational coupling, right? So this means there is no rho vibrational coupling, which means, in other words, your E dot is the energy of your translation plus the energy of your rotation plus the energy of the vibration. Okay, there's no coupling term, no cross term of vibration and rotation. All right. And so then following this separation, we can write our Q tot for this system to correspond to Q tra times Q rot times Q vip. Okay. Now, this means we need the partition functions for these energetic modes. The one partition function you already have seen is the one of the ideal gas law. If we now assume that your diatomic, again, for the purpose of the translational degree of freedom, is just like an ideal gas, so your diatomic molecules do not really interact with each other from far away. They look like an average mass particle. So we simply write again our 2 pi m over h square beta 3/2 v. The function you're all too familiar with by now. And now we have 8 pi squared over h square beta times I. So this is something you haven't seen yet. This is the rotational partition function, I being the moment of inertia. And then we have the vibrational partition function, which is written as e to the minus beta h nu over 2, where nu is the frequency of your vibration, right? Your two atoms, they will vibrate. And this is still divided by 1 minus e to the minus beta h nu. Okay. And that is your vibrational partition function. Okay. Again, as I already said, you still need to be a little bit patient. We will derive these partition functions soon. Right now, I'm just simply giving them to you, but do not be concerned. You will see where they are coming from. Now, of course, for your entire system, Q equals Q to the n over n factorial. And we can now go ahead and evaluate some function of state. So the most important, of course, always the energy for some gas of diatomics. Okay. So there's a huge step forward from some gas of monoatomics, monoatomic rare gas atoms, right? So this is our minus the derivative of logarithm q with respect to beta. And we can now insert the corresponding terms and differentiate them immediately. And so I think by now we have some practice here, right? This would be for the translational term. And then all those terms independent of beta die because I'm differentiating with beta. And I'm writing n or 1 beta for the translational part. And then there's another part where I had to differentiate once the numerator and then there's also still my derivative of the logarithm of 1 minus e to the minus beta h nu. And this one is simply so derivative of the logarithm of a function is 1 over the function. So I have 1 minus e to the minus beta h nu. And then I still have to differentiate the function. And 1 minus e to the minus beta h nu differentiated gives you h nu e to the minus beta h nu. Okay. Now I can rewrite this by making everything molar, right? And then I have 3/2 RT. Right. Now the beta being 1 over kBt, right? And then dividing by Avogadro's constant with the KB gives me the ideal gas constant. So this was the energy contribution from my translational degrees of freedom. And now I'm adding 1 RT from my rotational. And then I have a vibrational term where I don't have my KB. So I'm still operating with N. And there's still the 1/2 left, which I factored out, plus the ratio of e to the minus beta h nu divided by 1 minus e to the minus beta h nu. Okay. And this is the vibrational contribution. And now this is very beautiful. So you see that from the translation, we get 1/2 RT per degree of freedom, right? I can move in X and Y and Z. Here, I also have 1/2 RT per degree of freedom. Since it's a diatomic, I can only rotate in 2 directions. But if I rotate around the axis of the rotor, my system is invariant and it will not contribute. So we discussed the number of degrees of freedoms as a function of the dimensionality earlier on already. So this is such a case. So in total, these give me 5/2 RT. And then I have 1 degree of freedom for my vibration. Now, this is really nice because we understand the composition of the energy of the diatomic very well. And everything is obtained from quantum mechanics. And all symbols in here have meaning. We only have the Boltzmann constant and Planck's constant, which are sort of empirical, if you wish, right? So they are fitted to this universe. If there's some other universe, you might have other constants. The only miracle or mystery right now is where do these partition functions always come from? Okay. So are there any questions on this exemplification of how we can make use of the separation of the partition function? Yes, please.
If you're dividing through by the number of moles, shouldn't it be a Avogadro's number instead of just n?
Oh, in front of the vibrational effect, yeah, I think that's fair. Well, so hang on. No, I think it should be the per mole. So it should be N over Na, right?
But for the rest, because
is 1 mole. Yeah. Yeah.
If case n times Avogadro's number, right?
Yeah.
And then you divided the other terms by lowercase n, you're left with NaKB, which is R.
Right. Yeah. So yeah, N. So this could be the N would become Avogadro's number, and then it's 1. right? This factor.
Sorry.
If the n is Avogadro's number, it becomes 1 here, right? This fraction.
But for the other terms, did you not divide by lowercase n? Because
we did.
Yeah.
So we set n to be NA, and then we divided by NA.
Okay.
So no, yes, you're right. So it should be something like this. Yeah. Yeah. Okay. Further questions? Okay, so then let's now consider the individual partition functions. And we start out with the translational one. You've been itching to know where it's coming from. And for the purpose of the translation, we consider only featureless point particles, right? So in the example we just said before, we had actually 2 atoms, right? And that's not a point. But now for this partition function, we assume it is actually just a point, right? Now, that's not such a bad idea, actually, because if you imagine a bunch of, I don't know, CO2 molecules flying around, a minute fraction of this Earth's atmosphere, or N2 or O2, these are molecules that will only very weakly interact with each other, right? So the strength is in the internal degrees of freedom. So from the outside, it actually, it's not a bad idea to, or it's not a bad approximation. If you had a bunch of reactive molecules that you evaporated somehow, or you have a bunch of unreactive molecules you evaporated, and then you photoexcite them and they become super reactive. In such situations, of course, this would be a poor approximation. Okay, so we consider only featureless point particles without interactions. Then we can use the quantum mechanics of the particle in the box. Okay. And this you have seen already. So the solution, I will not show you how we get to the solution, but just to remind you, the solution for the eigenvalue in the x dimension is h squared over 8m, the length of the box squared times the quantum number nx squared. And this is the 1D particle in the box. Right? So this means our partition function for this x dimension is, just as Boltzmann told us, the sum over, and for the particle in the box, we start at 1, e to the minus beta epsilon x. And I have to absolutely specify the state. So I'm sorry, this is EXN. Okay. So we can insert this. E to the minus beta h squared over 8m x squared epsilon n x squared. Okay. Now, if you look at this function in terms of n, right, our variable, you can see that this actually looks like a Gaussian function where this factor here in front would be your width, sigma, right? So I can then say that I want to approximate this with an integral. And now I go from 0 to infinity. And I'd like to neglect the difference between 0 and 1, since my summation started at 1, right? And I'm integrating over n, and I integrate n squared over sigma squared. Right? So this is an integration over Gaussian, which means this is just with different symbols, 0 to infinity dx e to the minus x square over sigma square. And we know that that integral is square root of pi over 4 times sigma. Okay. So this whole integral then becomes pi over 4 times, and now my sigma must be the square root of my prefactor up here, inverted, right? So I need 8m lx square over beta h square, square root. Okay. Now I can pull these together. So the 8 and the 4 cancels. So I have 2 pi m, and my lx squared, I can pull it in front of the square root. Like that. Okay. So this again is with a small approximation on where I start my integral. If I should start really at 0 or at 1, I can do this. And I can hence consider my partition function in the x direction. Now, for the total tra, I would need to repeat this in y and Z, but there's no distinction between these dimensions. They are all energetically equivalent. And so I simply get the square root 3 times. So in other words, I now have to have 3/2 as an exponent. And I get my direction in the L. And that, of course, is nothing else than your volume. And so now you've seen how we have used the solution of a Schrödinger equation with Boltzmann's formula for the partition function to arrive at a closed form expression for the partition function, thanks to the integration of this Gaussian integral. Any questions on that? All clear? Yes, please.
Chris, why don't we consider the particle in the box or this one?
For the translation, thank you. This is, of course, a great question. Why is actually the particle in the box Schrödinger equation the relevant equation? So let's go from 0 to Lx. In here, the potential in your Schrödinger equation is 0. And then, as you know, at the walls, your potential becomes infinite, right? And this is a good model of a container, right? Imagine you have some container and your particle is flying around in the container and there's no interaction. This means it only has kinetic energy, right? So it's freely going back and forth, bouncing off the wall, right? Like billiard balls, you hit the wall, it's a huge potential, and then you come back again, right? And so we can, this is a good idea to a very fitting Schrödinger equation for the translation of your entire molecule. Okay. Does that make sense as an answer? Yeah, no problem. So you can literally imagine these infinite potentials to be simply the walls of the container in which you're studying your sample. And quite literally, for the particles inside that container, penetrating into the wall of your container is something which has a probability close to inverse infinity, right? So this is actually a useful application of the particle in the box case, right? And I don't know if examples were given to you where the particle in the box Schrödinger equation is useful for. This is one of them. All right, further questions? If not, we still have some time to enter chapter 4.3, where we would look at the rotational partition function, which we just exemplified above, right? So we are looking now at this part here. Now, before we enter here, we should make a clarification that for this one, there are internal features, right? And this is actually true for all degrees of freedom except for the translational ones. So the translational partition function, you could also use it for fullerenes, right? Imagine a container with fullerenes floating around. You can still use the translational partition function. But for the internal ones, we actually have these features, and this has an implication in the sense that our Q tot, the capital one for the macroscopic one, has a Q tra to the n divided by n factorial, because we don't distinguish featureless particles, but then they become distinguishable. So for the other degrees of freedom, we do no longer need the normalization by n factorial. Okay. So these guys here, these degrees of freedom are distinguishable. Okay. So maybe the easiest answer, the easiest example is if you consider, for example, the vibrations in a water molecule. Right? There are three vibrations you can have. If you imagine my head to be the oxygen and these two hands to be the hydrogens, right? Then you can vibrate like this, right? Or you can vibrate like this, or you can vibrate like this, right? And so you can clearly distinguish them, right? Now, in terms of, and I'm sorry, I actually forgot to mention that one thing I still wanted to point out, and that's actually part of the of this expression here, is the scale of RT. And that is 8.1 joule per Kelvin and mole times T. And at 300 Kelvin, that's 5/2 2,400 joules per mole. And so this is roughly 6 kilojoules per mole. What you get from translation and rotation. Now, if I break a covalent bond, how much do I have to pay? terms of energy, right? Does anybody know? Nobody? It's roughly 400 kilojoules per mole. Okay. So the energy you get from just moving and rotating around is roughly 1% of a covalent bond. Okay. And that tells you something, right? So in chemistry, we are dealing with many scales, right? And your chemical reactions, they actually connect, or they describe these very rare situations where you can actually create a channel from one minimum to the other, where ordinarily you would have to overcome huge barriers, right? So hence the entire magic of catalysts, right? But that kind of energy level, your 1% of a bond strength, right? That's sort of thermal noise that's floating around, right? So once you're getting there, your reactions will occur seamlessly. I'm sorry, I wanted to make that point earlier. So we started the rotational partition function, and we have a Schrödinger equation for rotation. The rotational Schrödinger equation for rigid rotors. And also here the solution is known. I hope, fingers crossed, you studied this already. If not, you will find plenty examples in the literature. The eigenvalue of the rotational state, J, is the quantum number J times J plus 1 h square over 8 pi square I, the moment of inertia. Okay. And this is also commonly written as hc, see the speed of light, b j times j plus 1, my quantum numbers, and b being the rotational constant. Which is typically measured in rotational spectroscopy. So this can be a measurement of your material, and it should correspond to h over 8 pi c times the moment of inertia. Okay. We have reached the full hour. Are there any questions? It doesn't seem to be the case. So we'll discuss the rotor some more next week, as well as the vibrational partition function. Thank you so much for your attention.